We're going to finish up the notes from last class, and we're going to look at the situation where in a triangle, three things. You know two sides, so let's say A and B, and you know the angle between them. So I'm going to use the Greek letter theta to indicate this angle. And anytime you have the situation, you can use this formula, but it comes back to sort of the basics. So the first thing we'll do is we'll go ahead and sketch the height in here, and we'll call that h. Okay, once we have that, we're going to just go ahead and focus only on this right triangle here and relate h to a and theta. So if you think about what that looks like just for that triangle, you can write the trig ratio sine of theta is equal to opposite, which is h, over hypotenuse, which is a in this situation. So you can solve for h, and we get h equals a sine of theta. So now let's go ahead and use the area for a triangle, which is 1/2 the base times the height, and we'll plug in what we know based on our picture here. So based on our picture, it's 1/2, the base is b, and then the height is a sine theta. Okay, so let's change this up a little bit, and I'll use this formula. We'll call this side C, and the side opposite, angle opposite of C, we'll call capital C. Side opposite of B, we'll call capital B. Side opposite of A, we'll call capital A. So the way we have it here is the area of this triangle was 1/2, and I'll switch the order here, A, B, and then sine of the angle between them, which happens to be C. So this is one way you can write the formula. And it turns out that it doesn't really matter which two sides you have as long as you have the angle between them. So for example, if you had side A and side C, as long as you knew the angle B in between them, you could say 1/2 AC sine B. And the easiest way that I like to think about it is all these letters have to always be different. So A, B, and C. Let's go ahead and apply that here. So 85 is the angle between. So the area is really straightforward. It's 1/2 times the 5 feet times the 9 feet times sine of 85. Okay, and one thing I noticed is some students, their calculators were in radians, not degrees. So make sure before you calculate to check that. This comes out to be about 22.414, and we'll use units feet squared. Okay, it doesn't matter if the triangle has an obtuse angle, you can just use that. So again, I have two sides and the angle in between. So it's just going to be 1/2 times 7 times 4, and then sine of the angle in between. And this one we get 13.923 inches squared. You know, if the numbers worked out cleaner, if it was like a 30, 60, 90, then we'd write the answer differently. But because these angles are not common angles we've studied, then we just have to write it as decimals. Next, we're going to go ahead and look at 10.4. And what we're going to do to just start to explore the idea is I'm going to give you two regular pentagons in this case. And I want to find two things. I want to find the ratio of their perimeters. That's one thing we're going to find. And I also want to find the ratio of their areas. Okay? So in order to find the ratio of their perimeters, we're going to need to find the sides. So let's do that. Okay, so we'll do what we did in class. We'll break this up into triangles, and this will also be 6. If you find the central angle, you know all the way around is 360. So if you take 360 and divide that by 5 triangles, you're going to get 72. Okay, so what that's going to help us to do is that's going to help us to get the bottom side here so we can find the perimeter. Okay, so we remember that that height that I drew cuts the angle in half. So this is going to be 36 in here. And we know this is 6, so I can go ahead and find this length x just using some simple trigonometry. In this case, I'll use sine, so sine of 36 is equal to opposite, which is x over 6. So you get x is approximately equal to 3.527. So then once we have that, we know that each side here is just double that, so I can just multiply that by 2, and I get 7.053. Let's do the same over here for this pentagon. Everything's the same, basically, except for the only thing that changes is this goes from 6 to 5. This is still 36. And let's call this, let's still call this x, but don't get it mixed up with the x over there. and this is a right angle. So take a minute and see if you can find x on your own. Okay, when I calculated it, I got 2.939, so 2.939 times 2 gives me 5.878 here for this length. Okay, so now I'm ready to calculate their perimeters, the ratio of their perimeters. So I'm going to find the perimeter of the one of radius 6 and the perimeter of the one of radius 5, and all I need to do is take the numbers I calculated for their side lengths and multiply by 5. So for the green one, I ended up with 35.265, and for the orange one, I got 29.38. Okay, you'll have to take my word for it, but you can actually simplify this with some rounding issues, and you get a pretty nice clean number. It turns out if you carried out all the decimals without rounding, that this ratio actually ends up being 6/5. So in other words, it's the same as the lengths of the radius. And this is true regardless of what side I gave you. It turns out that once I give you the length of a side of a regular of similar figures, then the ratio of their perimeters will be the same. Next, let's find their area. So the area of the one with the 6 radius and the area with the one of the 5. And let's do this a little bit differently. I'm actually going to use the formula we did earlier, where I just need the angle between the sides. So there's 5 of these triangles, and each area is 1/2, 6, 6, and then sine of the angle between them, which is 72. And the same thing for the orange one here. There's 5 of those triangles, and the area is 1/2, 5 times 5, sine of the angle between them. And here actually it's a little bit clearer. We're not going to plug it in or anything. We're just going to see what cancels. It turns out the 5s, the halves cancel, the sine of 72 cancel, and what you end up with is 6 squared over 25 squared, which is 36/25. So that's the ratio of their areas. So these two actually lead to a theorem about similar figures and the ratio of their sides and the ratio of their areas. So here we go. I know we've used the word scale factor pretty interchangeably, so we'll just kind of stick with the context here. So if I give you two similar figures and their scale factor is a to b, right, or you can think of it like a to b, then it turns out the ratio of their perimeters is also going to be a to b, right, or you can think of it as a or b. And the ratio of their areas, as we saw above, is actually a squared over b squared. Okay, and we showed that through that example, but you can really prove it if you want. Okay, so that makes this section super, super easy. So if you take a look here, the trapezoids at the right are similar. The ratio of the lengths is 6/9 or 2:3, so it's 2:3 ratio. So if you want to know the ratio of their perimeters, it will also be 2:3. And if you want to know the ratio of their areas, it's just going to be 2 squared to 3 squared, or 4:9. Go ahead and try problem 2, 3, and 4 on your own. Take a few moments, so maybe pause the video and then come back and check your answers. Okay, so for problem 2, I know the area of the small over the area of the big is going to have to be, the ratio will end up being 16/100. Okay, and I know that reduces, but let's not worry about it now. So it says the smaller pentagon is 27.5. Okay, so that's going to be here. We'll set up a ratio over, and then the bigger pentagon, we don't know what the area is. So we'll just call it A for area. So we go ahead and cross multiply. 16A is equal to 2500, and you should get that the area is approximately equal to 156.25 square centimeters. And again, that's just an estimate. Okay, so in problem 3, a group of high school students cultivated a plot of city land. It doesn't say what the shape is, and it doesn't really matter what the shape is. We can still answer the question, but let's just assume that it's a rectangle, so A to B. And so the area of this would just be A times B, right? But the next year, they're going to be given a larger plot of land that's 2.5 times as big. So this is 2.5B, and then 2.5a. So you can use some of the theorems, but I think it's just easier here to calculate the area. Works out to be 6.25 times the original area. So if we understand that they were able to make 13 bushels of vegetables here, then they should here make 6.25 times 13 bushels of vegetables there, or 81.25 bushels. Okay, so this one is asking us to work a little bit backwards. So I know it's 50 to 98, but that's the ratio of the areas. And we know that's going to be the ratio of the perimeter squared. So I'll call it P1 squared, P2 squared. Okay, so without doing any crazy math, to get P1 over P2, all you really have to do is square root this. So it should be square root of 50 over square root of 98. Now let's see if we can do any work to break that up. I know 50 is 25 times 2, so there's a perfect square there. So I can factor out a 5 and leave a rad 2. And then 98 is a little bit trickier, but we can think about it. That one is 49 and 2, so there's a perfect square there, so I can factor out that 7. The rad 2's cancel, and so in the end, you'll just end up with the ratio of the scale factor is just 5 to 7, which is the same as the ratio of their perimeters.